Sir Isaac Newton, 1642 to 1727, President of the Royal Society, is probably best known as the author of Mathematical Principles of Natural Philosophy, a compendium of experimentally replicable physical observations outlined and graphed according to mathematical principles. This work lays out Newton's three main tenets regarding motion. 1. Regarding inertia, an object, stationary or in motion, will remain in the same phase, stationary or in motion, unless or until acted upon by another force or object. 2. Regarding entropy, the multiplication of mass by acceleration equals the force of an object. 3. Regarding momentum, every object has an equal and opposite force, and for every action there is an equal and opposite reaction. Between the Principia's publication in 1687 and Einstein's Annus Mirabilis in 1905, these three principles were seen as the chief, utmost, and primary laws of physics governing the entirety of the visible cosmos. If any event could occur in the physical cosmos, it could be predicted exactly according to Newtonian models. At least, so was believed until Einstein challenged the Newtonian concept of gravity being solely a centripetal force, and asserted that a nearby object's gravity could warp the light emitted from a more distant object like a lens, creating an effect of stellar parallax. For the first two-thirds of its existence, the modern philosophical school of physics was Newtonian, and as such it was premised on the scientific method of hypothesis, experiment, and result, on the principle of Occam's razor, stating that if all other explanations prove false, a counterintuitive option may yet prove true, and on the principles of deductive logical reasoning in general. As a result of this, a great deal of credence is given in the modern scientific community to demonstration by replicable experiment. Anything that can be illustrated by some physical feat can more easily then be used as an example for another, larger, or even invisible force's impact on cause and effect. Newtonian thinking is therefore limited by belief to a more or less linear model for cause and effect. One domino or event impacts the next domino or event, and so on and so forth. However, without the kinetic exchange of forces between one object and another, cause and effect, should they occur, can only be inferred as resulting from the motion of smaller particulates in an otherwise invisible medium. However, this has not yet explained what distinguishes the quark-gluon plasma from the supposedly empty Hilbert space between atoms, or from the relative ether energy of the microwave background radiation that fills the depths of outer space. Because only direct effects can be measured objectively in Newtonian models, indirect effects, so-called acausal connecting principles, are more difficult to measure. Nevertheless, such apparently serendipitous coincidences continually occur in nature, and one can easily posit the anthropic argument that complex, multicellular living organisms could not have evolved from the primordial ooze without such an against all odds sort of occurrence. If Newtonian entropy is truly a universally applicable principle, then the earliest bonding of macromolecules into single-cellular protozoa, amoeba-sized microbes inside the nuclei of which were the original coded strands of DNA, being a negentropic process itself, could never have occurred. Therefore, for life to have evolved, Newtonian entropy must not be absolutely ubiquitous universally. In some places, there will arise closed systems of negentropy, from within the open system of entropy that encompasses and surrounds them. The standard model of essentially linear cause and effect based on Newtonian principles of physics depends on kinetic collisions for observations to be able to be made about otherwise invisible fields of force. Electrons orbiting atomic nuclei, for example, require collision with a photon in order to coalesce from a condition of uncertainty into a fixed electrical charge. Without such an example of transfer of force from one particle format of matter to another, it remains counterintuitive to the mind of a classically trained Newtonian physicist to think of an invisibly small, particulate medium permeating all matter as being able to transmit spooky action at a distance, or indirect interconnectivity between otherwise unrelated objects. However, apparently unrelated events occurring simultaneously to one another may share a common cause even if this cause remains shrouded from the naked eye. What we will be looking at in this presentation is how to physically, visibly, model the effect of an immaterial field of pure energy.